This is a review for the process control final exam. We are going to go through just an overview of the course and give a practice exam that we can go through together. If you'd like to follow along with the practice exam, go ahead and just select this link, or it's going to be in the description of the video, and this will bring you to the review material from the prior exams. So you can just select those, and it has a list of topics and a practice exam as well. And then for each of those you'll have the topics and a video with the practice exam. I'll select number 3 as well. Okay, so those are the topics to cover, and we also have in here an overview, a course map that shows how we go from starting with controller design all the way down to tuning a PID controller. So let's just go through that briefly, and then we'll jump into the practice problems. So we start with controller design right here at the top, where we select things like our actuators and measurements. And these are going to be things like a process diagram that indicates the location of transmitters and actuators. And then we also have things like block diagrams that indicate the flow of information in a control loop. So we have a decision right at the beginning whether we have data or not. If we don't have data, then sometimes we create a physics-based model that then we can linearize to come up with something like a first order plus dead time model. Or we can simulate that physics-based model, such as with a step test or doublet, a pseudo-random binary signal, or historical data. These are different ways to get with a graphical fit or regression, we can get first order models, second order models, or other these lower order models. We can also go on to decide if it's a linear model, and if it is, then we can use time series or state space, and if it's not, then we can use a physics-based empirical model, and that leads us to model predictive control. But we're not going to do that here. That's going to be the topic of a different course. So we're going to go mostly with single input, single output systems that are linear, and another example of a linear system besides the first order plus dead time is the second order plus dead time or higher order models. Okay, so this is in the modeling section. So once we have a model, then we decide if we have any measured disturbances. If we do, then we might add a feed forward to our controller. And if not, we decide what type of PID controller we want. We can have just the P only, a PI, or a PID. If it's an integrating system, then we're going to use a P only controller. Otherwise, we're going to use one of these other ones. We can do a stability analysis to determine what range of controller gains we can use, and then from there we can select appropriate tuning correlation that relates our first order model to the initial tuning values that we want for a PID controller. And then once we have those, we implement the control, and we determine if it's acceptable and adjust these tuning parameters, and then once it's acceptable, we monitor the PID performance. So with each of these blocks, we've covered material for each of these on how to design and tune a control system. And then in this area, this is the modeling area. Alright, so this is how to create a model, and this is how to create and tune a controller. Alright, so this would be, exam 1. We did a lot of material in the modeling area. Exam 2 was controller, and then exam 3 was the analysis of all of those with some detailed analysis on stability, on second order systems, on other things in both of these areas. So the final exam is going to include all of these. All right, let's go down to, we have the practice final exam, and then we'll have solutions to problems 1 to 2, and then I'll break the video up. Second video for problem number 3, which is also the same as one of your homework problems. But I thought it would be good to review that one because it's fairly comprehensive. Okay, so let's go over to the practice exam. It's just going to be a PDF on the course website. Don't forget that you're required to do 2 college lectures, so you make those up before the final exam so you can answer that. Alright, and then if I go down, I'll give you the Laplace table, so you don't need to include that on your note sheet. You'll have a total of 4 pages that you can use. Then you'll also have the class 10 pages that you'll create collaboratively. So I'll print that out and then include it with the exam, and then you can bring in your own 4 pages of notes. But we will have these, so you don't need to necessarily put these on your note sheet. Okay, so there's the Laplace tables. We also have a second order system, how we relate to things like rise time, peak time, overshoot, and zeta value. And then we have our decay ratio and peak time, that's period as well. Alright, so let's go on to the short answer questions first. We want to sketch the response of a second order system that is underdamped. And we'll indicate on our sketch how to calculate rise time, overshoot ratio, and decay ratio, and settling time. So I gave you the plot up above, but let's just say we didn't have that. We would do something like this. Here's an underdamped system. Here's our steady state value. Okay, so the rise time is going to be when it first reaches that steady state value, or in the case of a controller, when it first reaches the set point. Alright, and then the peak time is going to be right here, where the first maximum value exists. And then we have the overshoot ratio, this little segment right here, I'll just call that B, and this one A. So the overshoot is going to be B divided by A. And then the decay ratio, we have a little segment here, I didn't make it very big, but there's C. The decay ratio is going to be equal to C divided by B. And then the settling time is going to be, this total quantity right here. We're going to go within plus or minus 5%, and just draw a band here. And when it stays inside that band, then we say that that is going to be the settling time. So I didn't draw this very well, but let's say over here is when it finally stays inside that band, and then I'm going to say that this is my settling time. Alright, so this is just a graphical indication of some of the things we pick out on second order underdamped systems. So let's go on to the next one. Let's give 3 similarities of cascade and feed-forward control with feedback trim. So in this case we have, let's just do a table here. Alright, here's cascade, and then feed-forward control. And some of the things that we have are in both of these, like the measurements, the number of measurements. Cascade control is going to have 2 sensors or 2 measurements. Feed forward will also have 2, one for the feedback and then one for the feed forward element. So that's similar between the two. Both of them are designed to reject disturbances. Okay, so I'll just put a check mark here and a check mark here. We design a cascade or feed-forward controller when we can measure and isolate the disturbance and try to take a proactive approach to rejecting that disturbance versus letting it affect our final error. Okay, the number of actuators that we have. In Cascade we have one final control element, and also in feed forward we have one as well. So what are some of the differences? These are the three similarities. Cascade control, we have two PID controllers, versus feed forward we have one PID, feedback loop, plus a feed forward element to that. Okay, so that would be a difference. Also, there's other similarities and differences that you can put down as well, but there are just three. Alright, let's go on to the next one, which is better a shorter rise time or a smaller overshoot ratio. Now in this one there's no right answer. I'm just getting you to think about and discuss some of the trade-offs between the two. You might throw out some examples as well. So for example, a shorter rise time might be better for an automatic braking system, where you really favor the response time versus any kind of overshoot in terms of braking too hard. Okay. Also, a case where a smaller overshoot ratio might be desirable is where oscillation is a concern, such as reactor temperature control, where you would favor a slower response versus something that would get there quickly, because the overshoot might cause runaway or something like that. Okay, so we have the trade-off between shorter rise time, smaller overshoot ratio. It really depends on the application. If you can put something in here that shows me that you understand the trade-off between the two and that it's application specific, that will give you full credit. What does it mean to tune a controller? So we often start with a first order plus dead time system, and then that gives us our controller tuning parameters. And those are often just initial values based on internal model control or ITAE or other types of tuning correlations. But then we implement those and then tune them, so we adjust them up or down, adjust these tuning parameters to try to achieve some desired control response. And that could be a desired control response for set point changes or for disturbance rejection. So often the tuning correlations have different tuning parameters for set point changes or disturbance rejection. Often the disturbance rejection tuning parameters are more aggressive. Alright, let's go on down to this one. Is this following system feed forward? So we're measuring the temperature right here, and then our controller is then adjusting its opening or closing the valve. Okay, and is this one feed forward or feedback control? So this one is, even though the sensor is before the valve, this is still a feedback control system, because the thing that we are controlling, and right here you have a T here, a temperature, and then that temperature that you're measuring, those are the same values. You're trying to control that temperature and you're measuring that same temperature. Now a feed forward controller might be if you change that temperature transmitter or installed a new one right here and then tied in that information into the temperature controller. That would be an example of a feed forward controller. Okay, so the answer is no, that's not, and because we're measuring and controlling the same thing. Alright, let's go on to the next one. We have some Laplace transforms here, and we have an input function which is described right here, and this transfer function that relates the input to the output. I think I got some, see if I can adjust this. Okay. Alright, so Oh, it just went blank. Let me see if I can refresh this. I'm going to pause it for just a second while I get the exam back. Alright, we got it back. Here's our system. We have this transfer function where we have x of s that comes in, and then the transfer function, which is minus 2 over 5s plus 1, and then our output, which is y of s. So we have a certain signal here coming in, and we want to calculate what is our response going out if I gave it that, that signal coming in. Let's sketch the input function, x of s. And so this is a signal, an input signal. Sometimes we use u of s. We commonly use that to denote an input. But in this case, it's just x of s. And you can ignore the prime there. That just means deviation variables. We normally drop the prime, but just to be very clear that this is in deviation variable form, we put the x prime of s there. Alright, so let's go ahead and do all of these signals. This is going to be a ramp, and that is going to start at 0, and that is going to have a slope of 1. We have another signal which is going to be starting at a time of 2, and that's going to have a slope of negative 2. And then we have a third signal that's going to start at 5, and that's going to have a slope of positive 1. So when I add all of these together, let's go ahead and just sketch this out. I have a slope of 1. Okay, after 2 seconds I have something that starts with a slope of negative 2. So in this case it's going to go, it's going to cancel out the one that's continuing up. Okay, but only half of that, or sorry, it's going to be twice what it was going up, so it's going to have a negative 1 slope going down. And that's going to continue for 3 seconds until it gets to a value of negative 1. And then this final one over here is going to cancel out the negative slope. Even though it would continue otherwise, the positive slope that we're going to add to it is going to just make it level out. Alright, so here is x of s. You can ignore that there. If I wanted you, we could plot, you know, y of t later. So this is x of t, lowercase x, in the time domain, but we analyze that from x of s in the Laplace domain. Alright, so let's derive the final expression for y of t with this information. Okay, so we're going to start with you know, just multiplying. I'll take my transfer function right here. I'll have y of s equals, and then it'll be minus 2 divided by 5s plus 1 times x of s. Now x of s is right here. I'll just plug that in, and then we'll multiply this out with all of our terms. So minus 2, 5s plus 1. Alright, and then I'm going to have 1 divided by s squared. And I'll have minus 2 over 5s plus 1. And this one is going to be a positive now. And I'll just combine some of the terms. This will be 4. And then I'll have s squared. And then e to the minus 2s. And then finally we will have minus, and then this is going to be 2 divided by 5s plus 1. And again we have the s squared, and then e to the minus 5s. So now I have my signal y of s, and now all I need to do is take the inverse Laplace of y of s to get y of t. So in each of these, the thing that's common is I have 1 divided by 5s plus 1 times s squared. So I'm just going to do an inverse Laplace on this, and then I can just multiply it by the factor out front and do the different time shifts on it. So let's to do this, we need to do some partial fraction expansion. Alright, I have a repeating root here, so I need the A and then the B, and then I'll have C as well, and that'll be 5s plus 1. The reason why I have to do this is because this term over here on the left is not in my Laplace tables, but these are. So if I can get into this form with partial fraction expansion, then I can convert each of these individual ones. Alright, so now I just am going to select, well, I'll multiply it through first of all by the denominator, and then get it into the form 1 equals s times 5s plus 1 times a plus 5s plus 1 times b. Okay, and then plus, and now we have s squared times c. Okay, I can just select values of s, like s equals 0, and that's going to make b equals 1. Okay, because this term is going to cancel and that term is going to cancel, and s is 0, so there I'm just left with b equals 1. Alright, now I'm going to pick s equals -1/5, and then if I solve that, then I have that c, okay, because this term over here is going to cancel, and this term is going to cancel, and so I'm going to have -1/5 squared times c, and so that means c equals 25. Okay, let me clean that up again. Alright, now I can just pick another s value. I'll just pick s equals 1. That one will be easy, and it'll just give me 6a plus 6b plus c equals 1. Alright, that is going to then give me a value of a when I plug in the b and c values. A is just going to be equal to -5. Alright, so I can just plug each of these. There's my b value, I'll plug that back in there. Here's my c value, plug it in here, and a value there. Alright, now I have each of these terms that I can then convert back into the time domain with my Laplace tables. So I'm going to go back to the Laplace tables. Let's see if we can just find those. Alright, here is one of them. We have the ramp. Alright, and then we have another one right here. This one's just a little bit different than what we have because we have 1 divided by 5s plus 1. So we just need to convert that into something that is 1/5 s plus 1/5. Alright, so we're just going to convert it into this form so that our b value will then show up right here. Alright, let's go back to it. Alright, here we have it. Okay, so now the first term, let's just go ahead and do all of these terms. I'll do it over here. Our first one is going to be -5. That's just a step. And then we have the ramp, and that's going to be t. Okay, and then we have plus, and then we're going to have 5 e to the -0.2 times t. So we just took each of those individually, and then I'll multiply this by s of t. It's our step function, so it's 0 before that time, and then non-zero after. Okay, so that is the this is all of those multiplied out. Now I'll just multiply by -2, 4, and -2, and then apply the time delays at the appropriate point. Okay, so the very first term, I'll call this term 1, 2, and 3. There's term 1, term 2, and term 3. So term 1, we're just going to multiply this by -2. Alright, so that's going to come up with, okay, so I'm going to have 10 minus 2t minus 10e to the minus 0.2t. Alright, multiply that by s of t. And then I'm going to add to that the second term, which is minus 20 plus 4. Now I need to apply the time shift. T minus 2 plus 20 times e to the minus 0.2. Apply the time shift here as well. T minus 2. And that's going to be s of t minus 2. Alright, our final one now is going to be a plus, and then just the same thing as we had before, but now the time shift is just by 5. Let's see, I have to do a minus 10 here instead. Minus 10 times e to the minus 0.2 t minus 5. And that's going to be s of t minus 5. Alright, so this is going to be y of t, y prime of t equals this big expression, but we just had to convert one of them with the inverse Laplace, and then we just applied it 3 different times with different scalar value out front, and then also different time shift. Okay, so that's it for this one. The final one, again, I mentioned there's a separate video for that. I just wanted to redo this one. I know we had done it before for a homework problem, but it's a fairly comprehensive review of actuators, sensors, control loops, stability analysis, and so it encapsulates a lot of things all in one problem.